So the topic of this presentation is electrodeposited graded bandgap solar cells, an affordable manufacturing option for Bangladesh. So the basic outline of the talk, I say that mainly three topics I'll be talking about. One is very elementary physics of modern and next generation solar cells, because I believe that for the initiation of the understanding of this topic, it is important. And then I'll be talking about some affordable fabrication techniques. Those can be suitable for our country and the developing part of the world. And at the same time, at the end, I would basically like to talk about what our academia can do to accelerate this process. So at the beginning, I would start with a question: what is a cell? In physics, in chemistry, or in electronics, when we talk about a cell, what we basically mean is, in very general sense, a battery. And a very basic characteristic of a battery is that it has mainly two terminals. One has a positive charge amalgamated, and the other has a negative charge amalgamated into it. So that is basically a very basic structure of any battery, of any cell. There are two terminals, one positive terminal, one negative terminal, and when we connect it with an external circuit, that helps us carrying the electricity. For a solar cell, that pretty much reiterates, and in a solar cell, that same process of separating two different charges to two different terminals is carried on using very simple semiconductor junctions. So the semiconductor base, from the idea of semiconductor basic, we know that intrinsic semiconductors, that means the semiconductors which are not doped, has the Fermi level exactly in the middle of the band structure. When we say about band structure, we pretty much know that matters have two different bands, valence band and conduction band. So for semiconductor, the band gap is of a moderate height, and within that band gap, the Fermi level is residing exactly in the middle for intrinsic semiconductors. When we talk about extrinsic semiconductors can be of mainly two types, p-type and n-type. When we talk about p-type semiconductors, the Fermi level resides nearer to the valence band. When we talk about n-type semiconductors, on the other hand, the Fermi level resides nearer to the conduction band. So when we make a junction out of it, that means when we attach a p-type semiconductor with an n-type semiconductor, the interface creates a band bending because the Fermi levels come to the reference level and becomes the common level for the two. Is it really possible to mute the when the speakers are talking, with all due respect? Okay, thank you. So when this interface is created, we can see this band bending is created, and this band bending basically takes the electrons. If I talk about an analogy, the electrons can basically work like a water drop, which goes downward, and the holes can be analogous to the idea of a water bubble, which goes up. So because of this opposite direction of electrons and holes, the created electron hole pairs, which are created by the sunlight, can go to two different directions, and they can be amalgamated in two different sides of the cell. Same thing can be done with a PIN junction, where the I, or intrinsic part in the middle, only does the extension of depletion region, because the depletion region normally for a PN junction is less wide compared to a PIN junction. If I go to a simple animation, I can say if the Pi and N semiconductors are attached together, we can see that there is the there is a common ground created by the Fermi levels, and because of that, there is a band bending taking place. And due to the band bending, we can see this kind of a structure here. And when it is connected through an external circuit through a device, this actually completes the overall structure of a solar cell. And when the solar radiation comes in, the photon energy, it actually gives birth to an electron hole pair, depending on the energy that it observes according to the band gap of the material. And the electron flows downward, hole flows upward, and we can see that the device is running. So this is the very simple structure of a PIN junction solar cell. But there is a problem. The problem is, you see, the monojunction solar cell, that means when we are talking about one particular material and we are doping it with different dopants and making it N-type, I-type, and P-type, the band gap barely changes. So the band gap stays the same. And since the band gap is staying the same, it actually absorbs the same exact range of energy. And we know that the photons available from the sun can be of different energies. We can see from this slide that only 5% is ultraviolet, 43% in the visible range, and 52% is in the near infrared. So when we are talking about homojunction solar cells, not monojunction, homojunction solar cells, that means we are using only one semiconductor. What happens is we are actually absorbing a very small portion of the visible light. So that is actually the wastage of most of the solar radiation. So to get rid of this problem, there can be different ideas incorporated in the engineering of these devices. One is the tandem-based solar cells, multi-junction solar cells, and the other is the graded bandgap solar cells. I will be talking about the graded bandgap solar cells today. So the basic idea of graded bandgap solar cell is that the band gap for this kind of solar cells, and it's a multi-junction solar cell, of course, the band gap for this kind of solar cells, it actually decreases from high band gap towards the low band gap. If you take a look at this figure, the initial material used, it has a high band gap, and if I go to the last material over here, it's a low band gap material. But interestingly enough, this is not the only transition we are talking about in this kind of solar cells. Apart from the transition of band gaps, we can see a transition of conductivity type as well. If I take a look at the first window material over here, we are talking it. We are calling it window material because sunlight is basically going through this material first, so we can call this an window material. So in this window material, we can say this is a P-type window material because the Fermi level is nearer to the conduction band. And along the way, we can see it's actually transiting from P-type to I-type here in the middle. And then N-type here, the Fermi level is near to the conduction band. So for a graded bandgap solar cell, the basic structure is the transition is not only taking place for the band gap from higher to lower, but also the transition is taking place from N-type towards P-type, or the other way around, from P-type towards N-type. So that is the basic structure of the graded bandgap solar cell. So how is it helpful? It can actually absorb most of the solar radiation if we can incorporate the band gaps accordingly. And at the same time, it can actually incorporate another mechanism called impurity PV effect. That means if there is a low energy photon absorbed, it can actually elevate an electron to a defect level inside the material, and that defect level can actually hold the electron, and another photon absorbed can actually elevate it to the conduction band, and therefore it can actually give birth to multiple exciton generation instead of just one exciton per photon. Apart from that, there are other mechanisms that can be combined into this process. It can be impact ionization. What impact ionization is, when it's more like a stone falling from top of the hill. When it's actually coming down, it can actually impact other stones and other pebbles as well on its way, and it can actually take them with it. So that is exactly what's happening here. And at the same time, there is another thing which we talked about, which is the impurity PV effect. Heat from the surrounding or small energies can be absorbed, trapping the electrons, and another electron can actually take down those trapped electrons using the impact ionization. So there can be impurity PV effect, there can be impact ionization individually, and there can be a combination of impact ionization and impurity PV effect. So therefore, we can see that it can actually create an abundant flow of carriers if we can incorporate the graded bandgap structure into a solar cell. Now, that was the concept. Now, if I come to the real life, when we do the fabrication, it is not always possible to do or to incorporate so many different layers. It will be possible maybe someday, but for the time being, we can say, if I take a very simple structure, this is how it will look like. And this structure in here, if I see here, this is as a window layer. It is used. It is using an N-type cadmium sulfide, which has a band gap of 2.4 electron volt. On top of that, there is an N-type cadmium telluride deposited, and on top of that, there is a P-type cadmium telluride deposited. So, taking a look, you can see this basically, it's not as good as the previous model that I have shown, but this has a graded bandgap structure. And this device has been fabricated in my group, and it has been giving since 15.3% efficiency, which is a decent efficiency for lab-based device, I would say. So when it comes to depositing, how we deposit it? We deposit on glass, and the glass is normally covered with FTO. FTO is fluorine doped tin oxide. So fluorine doped tin oxide is nothing but any other transparent conductive oxides. On top of that, we deposit cadmium sulfide, which has a band gap of 2.4 electron volt. And then from N-type, we transit to P-type, to N-type cadmium telluride, having a lower band gap of 1.4 or 1.5 electron volt. And on top of that, we deposit P-type cadmium telluride. So if we see, it basically transits from N-type through, so there is an N and P type transition. So it goes from N-type towards P-type, and at the same time, the band gap decreases from 2.4 to 1.4. And on top of that, when we deposit the metal contacts, we can see this is the finished device that we make in the lab. So due to the discussion of the fabrication, we now know that using some way we fabricate it, we deposit these semiconductor layers. The question is, what are the different deposition techniques? There can be many. There are high vacuum, high temperature techniques, and there are physical vapor depositions, chemical vapor depositions, magnetron sputtering, ion beam sputtering, pulse laser. All these different deposition techniques are actually high vacuum and high temperature techniques. There are advantages, of course. High quality fabrication can be done. The quality of the semiconductors are really good, very less defects. And at the same time, there are some disadvantages. One is obviously the expensive nature of these techniques, because whenever we talk about high vacuum, high temperature techniques, the price goes up. And at the same time, there is another set of problem, which is the mass producibility, because often these high vacuum, high temperature techniques cannot really be translated into an industrially viable section. So therefore, what happens is these disadvantages can actually take down the productivity of the industrial process. So there are low cost, low maintenance techniques as well. Spin coating is one of it. If I talk about the advantages of it, of course, the low cost and the quick nature of it is good. But at the same time, the quality of the material is not very satisfactory. And for producing it in large amount for the industrial production, it's often not very suitable. So therefore, we basically need to find out a way which is in between these two, which is not very expensive and at the same time gives high quality fabrication as well. Then comes the idea of electrodeposition. So the electrodeposited solar cells can be a very affordable way for especially the developing countries like us. And the technique is quite simple. I sometimes oversimplify it, saying that we can literally make solar cells inside a beaker, or like if I say inside a balti, if I say in local language. So for electrodeposition, we need basically two different electrodes. One electrode is the working electrode. Normally we use it as a cathode. And then there is an opposite electrode, which we use it as an anode. And most of the cases in the cathode, we attach the working sample on which we want to do the deposition. And in the deposition electrolyte, if I give an example, let's say we are depositing cadmium telluride, we can mix a cadmium source, and the cadmium source, let's say, is cadmium nitrate, which will give away cadmium 2+ ion. And for the tellurium source, we can use tellurium dioxide. And this can give argent tellurate ion, and that these two positive ions can be actually attached when there is a flow of electricity here, can be attached to the negative terminal, because cathode is the negative terminal. These two positive ions can come, sit on it, and create cadmium telluride on top of this sample. So this is how simple it is. I will show a video very soon, but before that, I would basically like to say why this electrodeposition technique is so good for countries like us. Of course, the very cheap nature of it is one advantage, and at the same time, the material quality is almost as good as vacuum method after some post growth treatment. It is a tried and tested method. In my lab, there has been 15 different semiconductor material that has been so far successfully synthesized and characterized. So it's quite tried and tested. A huge range of semiconductor materials can be synthesized using it. It is commercially successful already, because British Petrol back in mid-90s and up until 2001, they have actually produced commercial grade solar cells using this technique. Unfortunately, due to the shift of their business nature, they have actually shut down their solar venture, so they do not use this excellent technique anymore, but it is a tested technique for industry. And to be more specific, it is industrially tested, and right at the moment, this is one of the only two commercial methods that has been industrially successful so far. There is another one called, it's basically a modified CSS method, which is used by the First Solar in USA. They are commercially successful, and it used to be used by BP before, and that is the only electrodeposition used to be used by BP before. So that is the other commercially successful technique. So I would say, if I talk about lab-based research, it is a successful method because I myself have done it. And if I talk about the industrial application of this technique. It is also successful because British Petrol has done it way before. Now, I'd like you to watch this video just to understand how simple this technique really is. So I would play it. It's a 2-3 minutes video. Please watch it. Thank you.
We are basically going to use this as a cathode, which is basically getting connected to the negative side of the cell. So what we do for this is we use one cathode and one anode. So let's put this carbon electrode. This is the anode we are using, and this is once again a carbon electrode, but we have attached a glass covered with FTO. I can see here a glass covered with FTO, and we have attached that with this carbon rod using a PTFE tape. This PTFE tape is very easy to find in the market. These are used for like sanitary works, for your bathrooms, to fix taps and things like that. So this is very easy to find. Carbon rod is nothing but graphite rod. So we basically can get this kind of a system. So this is our cathode, and on top of this FTO layer, FTO glass, we are basically going to grow our cathode. So we are basically going to attach this electrode with the cathode. This is the cathode, and this is our anode. The next thing is make sure that both electrodes are touching the electrolyte property. So if you can see here, maybe from this side, this is the cathode, which is basically connected to the sample, and this is our anode, which is inside the submerged inside the electrolyte. And then we are going to fix the voltage. Here, this system, we call it a potentiostat. The main work of it is basically supplying a voltage and measuring the current because of the supplied voltage. So the voltage that we are going to supply to that is minus 1.330, which is 1330 millivolts. It's a very small voltage, and the moment we have actually put that in, this ammeter, this is an ammeter. This ammeter is basically measuring the current due to the applied voltage. So this is the applied voltage across the two electrodes. This is the measured current due to that applied voltage through the electrolyte. So we can actually try to grow the sample for few minutes and actually see how the sample actually is looking like. So we will show you the final result. So we just need to wait till the deposition is over. Thank you very much.
So after this setup was done, we have waited 10 minutes, and after 10 minutes, this is how the sample is looking like. The transparent sample that you had seen before, this is the look of it after 10 minutes. This is how it looks after we detach it from the electrode. So we can see that this is such a simple technique, just by supplying a voltage and seeing the deposition on the FTO layer. And the nano structure that is actually structured on it basically works based on the FTO layer, because normally even if it sees like a smooth surface, there are actually peaks there, and the high electric field gets created when the electric connection is given. And on these high electric fields, cadmium telluride starts growing, and there is a nanorod type of growth takes place. If I take a look in the cross section here and the top view, we can see after some time there is all. And from the AFM, we can take a look that these rod type nanostructures, are visible from the AFM for cadmium telluride. And for the top view, I can say that two-dimensional ACM image almost shows the similar image as the top view that is animated here. So this is how the nanostructure gets created on top of the FTO layer. So this is how the electrodeposition works, and this is how layer after layer we can deposit one top of one another and make a complete device out of it. But there are some questions we need to answer first. One is, at which voltage do I need to grow the electrode or electrodeposit the layer? So we basically need to have that answer, that at which voltage do we grow. And at the same time, we need to basically find out after the growth, what type of material is it? Is it N-type material, P-type material, or I-type material? If you remember the graded bandgap structure, we need to understand what type of material is it to actually fabricate the device structure as planned. And another question is the band gap. We need to find out the band gap of the grown materials, because that is also important for structuring the graded bandgap solar cell. So these are the questions that can be answered. I basically want to discuss very briefly about those. To find out the answer of the first question, we can use a system called potentiostat. I have already talked about it. And cyclic voltammogram can be done with a potentiostat, from where we can find out a range between which voltage range we need to grow samples and characterize to see whether they give us the optimum characters. And at the same time, I also need to tell that a potentiostat is commercially available, as well as a potentiostat can actually be made easily using microcontroller based systems. Nowadays, microcontroller based systems are very available, and I'm quite sure students from undergrad and postgrads can actually make a system out of it. So potentiostats can actually be made at your own lab using Arduino microcontroller even, and can help you electrodeposit solar cells. Then the question is, how do we find out the conductivity type, N-type, P-type, and I-type? There is a very simple setup called photoelectrochemical cell measurement setup. And in this setup, the main thing that we do is basically we measure the voltage across the two electrodes, where one electrode is the deposited layer and the other electrode is just a carbon electrode or graphite electrode. And we basically measure the short circuit voltage between them under illuminated condition and under dark condition. And this difference of voltage can give us the direction about what type of material is it. If the difference is negative, normally we find out that the material is N-type. If the difference is positive, we find out the difference is P-type. And if there is barely any difference, then it is merely I-type or intrinsic type material. So it is once again a very simple technique, and it can be set up at any lab. It does not require a clean room. It does not require any sophisticated setup. And for finding out the band gap, the most widely used technique is the UV visible spectrometer, where the TOC plotting can give us the band gap. This UV visible spectrophotometer can also be created from FYI, or sorry, DIY or do-it-yourself method, where off-the-shelf materials can be used. When I used to teach at Bangladesh, three of my students have basically made one spectrophotometer out of very ordinary materials available around them. And the paper and the poster is actually attached in this lecture slide. After the presentation, if anybody is interested to take a look, I can actually email the slides to you so that you can find out the paper and poster. Apart from that, UV visible spectrum photometer is, to the best of my knowledge, is available in Energy Institute of Bangladesh Atomic Energy Commission, BCSIR, the Red Green Research Lab at Pantupot, and many more places and many more universities as well. So it's a very common device, common instrument for measurement, and people, if people can actually delve into collaborative research, it is possible to characterize for all these three major parameters, and as long as the synthesis is done, it can be done inside the country as well. So what can our
Dr. Ashfaq, maybe we have time constraint.
Yes, I am finishing as soon as I can. Just give me 5 more minutes.
Okay,
great. So the question comes often when we talk about cadmium telluride based solar cells is it's toxic. Why do we use it? So I would basically like to very briefly answer those. One is it's thin film based. That means it uses a very less amount of material. So a very little amount of cadmium telluride is being used. Silicon, which is the major material for solar cells, is mainly mining based. It is mined. But cadmium telluride, 100% cadmium is actually coming from byproducts of different industrial processes. So cadmium is mainly a byproduct based material. It produces, cadmium telluride produces the cheapest solar electricity per watt. So far, that is the world record for any solar cells out in the market. It produces the cheapest electricity per watt. And the manufacturing emits the least amount of greenhouse gas. And at the same time, the payback time is also very less. In fact, it has the lowest energy payback time amongst all the solar energy material. So because it's byproduct based, it just only making cadmium telluride based solar cells not only increases the renewable energy supply, but it also decreases the chances of cadmiums going freely into the environment. And electrodeposition, once again, I would like to say that it is very friendly for the industrial application. And if I take a look at this picture at the right, this panel is basically the panel made by British Petrol I talked about. And these panels were actually in market up until 2002 for purchase, but unfortunately they have exited. And our academia can actually help students and themselves by actually working on the simulation and modeling of solar cells based on graded bandgap device architecture, because it's a very unique device architecture. At the same time, universities can basically get specifically these two books in their libraries. These are specifically written for thin film solar cells based on cadmium telluride using electrodeposition technique. So this can be availed for the students and faculties, and they can be very much assisted by it. Undergrad students can arrange projects for different instrumentation development, as well as for synthesis of semiconductors using electrodeposition. And faculties can write grant applications based on the ideas talked about, and set up fabrication labs with much more affordable budget compared to any other fabrication techniques available. So, and the research philosophy of going for cutting edge research can actually also be changed with using local instrumentation and local technology. And please feel free to email me if you have any other questions, and if you need the presentation slide that I have just presented, email me in either of these email addresses. I would try to get back to you with the presentation slide and any question that you that you need answer of.
Thank you very much, Dr. Ashfaq. Professor Saleh.
Thank you, Dr. Ashraf, for your nice talk. So we have time limit. Maybe we can accept one question. Maybe Dr. Shohid Jaman can ask your question. Okay, unmute. Dr. Robani, please. Unmute Dr. Shohid Jaman.
Yes, done.
Thank you. Thank you very much. Thank you very much for your nice presentation. I'm Mohammad Shahidul Sir from Kanajo University, Japan. Actually, I have very simple questions. So there are two questions I may ask you. The one is related to your
Dr. Shohid, if you can raise your voice a little bit, somehow I'm not really being able to hear you very well.
Sorry, I'm sorry for that. So I have a very simple basic two queries. So one is related to your electrodeposition. So how about actually I had the long experience with the chemical bath deposition technique.
Right.
So actually though we can make the film with low cost, if you consider about the cost, that can make the very suitable, really the good film. But problem is for the reproducibility. So that's why I'm asking you personally, how about the reproducibility for your, like you are using the electrodeposition? That is one. And another one is like you explain actually the like, say for example, like what can be the optimal graded band gap for solar cells that which can reach the SQ limit, particularly related to the graded based solar cells.
Right. Excellent questions. The first question is about reproducibility. And I absolutely agree with the person who's asking the question that reproducibility can actually be a matter. And it's a matter of concern for us in the lab as well. But like I told you, it has been industrially tested by BP, and BP has actually commercially produced 11%, 12% efficient modules using the electrodeposition technique. In our lab, we have found out that we can reproduce 15%, 14% efficient cells in the lab-based devices. And the reproducibility is possible, but we have actually seen 18%, 18.5% efficiency as well, but we could not really reproduce those. So I agree with that fact that reproducibility can be a question, but there are many parameters. Those needs to be very carefully maintained and managed in order to basically keep the reproducibility at a level so that it can be used commercially. And like I have already told, since it has already been implemented commercially, I can say that for electrodeposition, the reproducibility can be maintained at an optimal level, and it has already been done. Next question was about the shock liquefier limit. So far, I can say we still did not do any simulation work. Like I told you, I am an experimental physicist. I cannot really, I did not really have a lot of experience about simulation. That is the reason I have actually talked about this idea of faculties and students getting into the simulation work based on the graded bandgap device structure. So for finding out the ability of these type of devices, up to what percentage we can actually convert the photons to the electricity, and how good we can actually overcome the shock liquefier limit, is basically a question that should be asked by someone working on the simulation. Unfortunately, I am probably not the best person to answer.
I am sorry for that. Sorry to interrupt.
Okay.
Actually, the cadmium telluride solar cell can be considered as a second generation solar cells or thin film like the solar cells. So say for example, in our cases, we are really focused on the perovskite type of solar cells or disynthesis type of solar cells.
So,
what we did, like we can tune easily the band gap, like A cation, B cation, or halogen. If it changes the A cation,
right,
definitely we can tune the wavelength, that the light, like we can change this from like the visible light to infrared light, right? But
yes,
while we combine say for example the tantalum perovskite with silicon, then
Dr.
we can
Shohid Jaman, we have a time constraint. Please
sorry.
discuss discuss after that seminar.
sir,
It would be
sir.
better. Thank you very much, Professor.
Dr. Shoaib, you can email me at
Yeah,
the
that
Yeah,
would be
sure,
nice.
sure, sure. Thank you, Dr.
Okay.
and we can
Uh,
actually carry on our discussion later on. It was
Yeah,
really
sure,
Okay.
sure, sure.
Dr. Ashfaqi Alam,
lovely
I am
discussion.
not going. I am not going inside of your talk because of
No, no,
timing.
it's okay. Thank you.
However, you have a comment like fabrication of large-scale solar cells in Bangladesh can reduce the cost of modules by more than 30%. This is
Yes.
very encouraging indeed.
Yeah.
And in addition, we should also search for more cheaper solar cells like dye-sensitized solar cells, quantum dot sensitized solar cell, what Professor Jamaluddin is doing there also for Bangladesh. Thanks a lot for your very excellent talks. And now I would like to request Professor Rabbani for give you the plaque of honor or plaque of gratitude. Thank you very much. And I am handing over to the Professor Rabbani, and thanks honorable audience as well as all the honorable speakers to allow me here to be with you, and see you again once again. Thank you very much. Allah Hafiz.
Okay, thank you so much, Professor Dr. Mohammad Nijamuddin sir and Dr. Yajid Saleh Ahmad. We have already displayed the plaque of gratitude to Dr. Ashfaq Alam. Please receive it, and I am requesting requesting to show the plaque of gratitude to our chair and co-chairs.
Thank you
Yeah,
very much.
thank you very much.
Thanks a lot for inviting me, and thanks a lot for giving me this opportunity of hearing so many learned colleagues of mine and giving me the opportunity to talk about my personal works as well. Thank you very much.
Thank you.